still the same question, right? So we're modeling two competing species, and the question is whether they are going to coexist. So notice that the change as compared to the previous example is that we increased the coefficient at xy. So both of them are bigger than in the previous example. So in other words, the competition became fiercer. It became so more intense. So still we can find equilibrium points, right? So we equate both x prime and y prime to 0. And then the interesting equilibrium point is when both x and y are positive. So we can just cancel by x and y respectively. So it is a linear system, and the answer is 10, 5. There do exist other equilibrium solutions. And since the part with x, y, x squared, and y squared is the same, the other equilibrium solutions are just the same as in the previous example. So they're just 0, 0, and carrying capacity and 0. So let us look at the phase portrait. So now notice that the picture is entirely different. So now this equilibrium point at 10.5 is not stable anymore. So it seems like a saddle point. So and what we see is that depending on the initial population, so some trajectories they eventually converge to 0, 10, and some trajectories they eventually converge to 30 and 1/3, 0. So let us see if we can confirm this analytically, right? So let us calculate the type from the Jacobian matrix. So again, what we do is we find the Jacobian matrix, meaning that we differentiate the first and the second right-hand sides of the system of differential equations with respect to x and y. And then at the critical point, we compute the specific Jacobi matrix, and then notice that its determinant is negative. So if the determinant is negative, then it is indeed a saddle point, right? So and since this is a saddle point, it means that it is not stable, and moreover, trajectories they have this behavior. They approach the saddle point and then go away from it. But at the same time, we can analytically confirm that these two other critical points, this one, right, when x is at its carrying capacity and y is 0, and this is when y is at its carrying capacity and x is 0. So both of them are now asymptotically stable, meaning that trajectories in the neighborhood converge towards them. But then, of course, it's just logically that what we are going to have is that some sort of the whole plane is going to be separated in between two regions. So in this region, so everything is going to converge to this critical point, and in the other region, everything is going to converge to the other critical point. So which actually means that depending on the initial condition, depending on the initial population, one of the species is going to die out. But who dies out and who survives depends on their initial population.